Hello everyone, am I audible? If I am, please type Y in the comments.
Yes,
Yes, that's fine. So then we'll proceed with uh, techniques, machine learning techniques for speech applications. So today and tomorrow we'll discuss something called dynamic time warping. On Friday you have the minor one exam, and next week we'll start what is known as hidden Markov model. So let me give you a brief overview or intuition about what dynamic time warping is. So uh, I hope my screen is visible to you. Let me check if I've shared my screen. Yes, okay. So what we are going to discuss is called dynamic time warping. This is a technique used primarily for speech recognition. It's a very simple technique and generally works, let's say, satisfactorily uh, for clean speech if the speech signal is not corrupted by background noise. And it's a very, let's say, old technique. It's I think 1970s or 80s it was first implemented on speech processing. It comes from something. This technique comes from something called as a traveling salesman problem, which is solved by something called linear programming. So this DTW has its roots in linear programming, and it was implemented in speech recognition in the late 70s or 80s, something like that. So what happens is when you speak, suppose you uttered a phrase, some phrase, sun rises in the east. This is a phrase. Let's say you uttered a phrase, a sentence. Now, your objective is to identify this phrase or sentence whenever it is spoken by whoever it is spoken. We are not concerned about who is speaking, we are just concerned about that this is being spoken. This phrase is being uttered or spoken. Now, every person, when he or she will speak, obviously there will be certain differences, but overall, compared to, let's say, some other phrase, whatever random phrase you have, some random phrase you have, compared to that, there will be much more similarity between all the utterances for this phrase. Some speaker one has spoken this phrase, speaker two, speaker three, this phrase they have spoken, same phrase. Now these will have quite a lot of similarity compared to, let's say, if you compare speaker one, sun rises in the east, and speaker two, some sun sets in the west. If speaker two utters sun sets in the west and you compare with sun rises in the east, there will be a lot of difference compared to, let's say, both speaker one and speaker two, if you are comparing their utterances and both are saying that sun rises in the east. So DTW is also called as a, or also called template matching. Is also called the templates matching technique. So what we are trying to do in dynamic time warping is match or find out the similarity between two speech utterances. Any two given speech utterances you take, you try to find out the similarity between them. Now, let's take an example. Let's say some Google Home is there, or Amazon Alexa is there, or something. This kind of. What else is there? Google Home, Amazon Alexa, then Siri, yeah, Siri, and all these appliances that you have, or even mobile apps you have for all this application. So you give certain phrases or commands. They have a fixed set of phrases and commands. So in your home or your friend or anybody could speak those fixed set of phrases and commands, and they could compare. They have certain stored phrases, fixed set of stored phrases that is a fixed, and whenever you utter and a particular phrase and it matches with, let's say they have five sets of phrases, one, two, three, four, five standard utterances they have kept stored, and they compare and they find out which one is having the, and you speak something, you are speaking one of the phrases, let's say a speaker speaks something, and if it matches any of the phrases closely, then that phrase will be selected and the corresponding command executed. This is one simple way to do it using dynamic time warping or template matching. So here is how it goes. So tomorrow we'll discuss it in a little more, let's say, depth or this one. But let's get a very simple overview of the thing. So you spoke a utterance, something you spoke, let's say one, utterance one, or you could say signal one, S1T. Someone else also, let's say, spoke the same utterance, S2T. Let's put S1T here, S2T here. Now, obviously, these are digital signal, everything as a fixed. Imagine you spoke for 1 second, the same thing you spoke for 1 second, because everybody has a different rate of speech and so on and so forth. And the other person spoke for 1.2 seconds, same thing, same utterance, same phrase, and all are, let's say, at 8,000 hertz recorded. So S1T will have 8,000. If I this is 8,000, length is 8,000. You can say 0 to 7,999 samples. You can put it like that. You can say 1 to 8,000 or 0 to let's put it 0 for your benefit. 0 to 7. 8,000. And what will be 1.2? So 1.2 into 8,000, how many samples? So 1200 into 8, 16. So 9600. So 9600 samples are there. So let's say 0 to each of them have some values. These are all values, these are all numbers. So you can have all these numbers here. Okay, let's use another color to say this is 0, 0.5, 1, something. Each of this. I wanted to use a different color, but what happened? 0, 0.5, 1, something. So each of them, all these values, I am putting it here, listing it here. Ideally, these are all numbers, nothing else. Similarly, all these are all numbers. We can put it here, 0, 0.1, something. These sample values, we are putting it here. Now our goal is to find the best one-to-one correspondence between each of these points. This value, this value come 0.1 here or 0.11. To find the one-to-one correspondence between the two templates, between the individual samples of the two templates. That's the goal. So what you will have is indirectly you will form a big matrix. You'll form a big matrix. What will be the size of the matrix? In this case, 8,000. Sorry, 9600. Yeah, 8,000 into 9600 in our case, in this specific example. And each of these matrices will represent a certain distance, certain metric, certain distance. And our goal will be to find a path of least resistance, or path which gives the least cumulative distance, the minimum or least cumulative distance. Can find a one-to-one correspondence. So DTW is a technique which will find you the best or optimal path. It will find you the optimal path to match two given templates, two given data templates, or two given signals. To match them, DTW finds the optimal path between them. So what I will do is I will show you a video. It's a very simple video, but it helps you grasp the main idea of dynamic time warping. So I will share you the link now. Then we will discuss the things that are discussed here. Okay, I will continue. So what was happening is, so I will give a very simpler example. It was a big matrix that was shown. Just assume that you have two perfectly, uh, let's say 1 2 3 4 5. Let's put it like this: 1 2 3 4 5. Okay, 1 2. This is all our 5. Okay, this is time. This is S1T. Again, another one is there: 1 2 3 4 5. Exactly same. Just imagine two exactly same signals. Signals which have independent variable as time are called time series. There is nothing fancy about uh, that term. Nothing special about that term. Anyhow, so these are two time series or two time domain signals. Now both are having the same. Let's put it like this. So we have 1 2 3 4 5. Let's say this is S2T, this is S1T. It does not matter which way you put it. So you have these are the numbers. These are the actual values. So you can here. I will try and use a different color. This S1, this S1T and S2T, each and every point you can find some distance measure. You can find an Euclidean distance, or there are many other distance measures that you can use. But we will stick with the simplest one, the Euclidean distance. So this point one, this point basically, the first point, you compare with each of them. So you get a value, some distance. So here it will be 0, this will be 1, this will be 2, this will be 3, this will be 4. Same thing: 1 2 3 4. You got it. Now you already know this. Again, you can compare. Let's say this point 2. This point 2 again, you can compare with all this. Indirectly, you will find that you are comparing point 1 of the first series with all other points in the second series. It's the same thing. If you compare any one point with all the points of the other signal, and indirectly that also means that you are comparing all the point any one point of the first signal with all the points of the rest. So anyhow, you can find a matrix where every point you are comparing what every point, every sample point of S1T is compared with every sample point of S2T. This is what you are doing. This is a raw thing. This is a simple thing. So let's put it here. The simple in the corner, I will put it. Let's say so. 2 here equals 0. These will be all 0 here. What will be this? This is 1 2 3. I think it will be something like this in this case. So these are all comparison between different points. So you're basically finding S2t minus S1t some distance for all t, for all value sample points t that are there, you are comparing. Or indirectly, t is generally a continuous time, so let's put it Sn. This will be for all n. This is just a very simple example I am giving. So now look, so we have now you want to traverse a path, we want to find an alignment, we want to find out which point is aligned. What is the job here? Let me put, what is the goal, which point or points of S1t are aligned or indirectly can be matched with which points of S2t. Find out which points of S1t are aligned or can be matched with which points of S2t. That is the goal. So here we will have let's go back again to this. So we'll have three different, in DTW we have, the name is dynamic time warping. Okay, we'll have three parts. We could have more parts, but the simplest one will have three parts. So from any point in a matrix, from any point, let's take this point, you could have a path. You have to see backwards. You could have a path like this, horizontal. You could have a diagonal path, or you could have a vertical path. Based on the distance, we are trying to find out the minimum distance. If the minimum distance obviously will happen if all the points are perfectly aligned, or they are the best aligned, the most optimum alignment occurs. So we'll consider this first case where there are only three parts, simplest form of DTW, where any point you can reach from three other points based on this part 1, part 2, part 3, part 1, part 2, part 3. And uh, you can also give some this called um, emphasis on the point. You could say, suppose part 1 and part 2, for we'll see what happens. Suppose part 1 and part 2, it seems like they get equal values. Then you could say that then part 1 is the most likely. You could give some weightage to each of these parts. But that's a different thing. Those are more complicated forms of DTW. But let's consider this. Just keep in mind this. So now, here, here. So to reach this point, you could reach from here, you could reach from here, you could reach from here. There are three options. Now I already know here it's 0. It's 0. So, but you have three options from where to reach. This is called, so from this simple matrix of distances, you can create a cumulative distance matrix. This is a simple distance matrix or one-to-one distance matrix. You have to create a cumulative distance matrix, and we'll see how to do that. Let's go. here. So we saw like this: 1 2 3 4 5, 1 2 3 4 5. So what did we get? Let's put like this: 0 0 0 0 0, and I think, yeah, 4, yeah, got it. So 4 2 1. So this is your simple distance matrix. Now let's try and figure out the cumulative distance matrix. So this is the easiest part. So you have this. Now to reach point C, our goal is to reach from here is the first sample point to the last sample point. This is the last sample point of both S1T and S2T, and this is the first sample point of both S1T and S2T. So this and this, they are fixed. You have to traverse from 0 0 to whatever is the uh, whatever is the m minus 1 comma n minus 1. If it is a different number of samples are there, in our case it's both the same, so we'll say 4 4. From 0 0 to 4 4 we have to reach. This is fixed. Your path has to start from 0 0 and end at 4 4. So in this process, let's see how to do it. See, here we know cumulative distance 0. It starts from 0, nothing to do. Here to reach this point, you could have three options. To reach this point, you can like this, like this, like this. Now see these two parts, there is nothing. There is nothing. This is the starting of the matrix. So there is only one possibility. So this one, whatever is there, 1 plus whatever was the initial distance, 0. Even you could say from here, 0 is there are no parts because this is the start of the matrix. So it is 0. For here, for this point, there are 3 paths available. 2 of them are non-existent, even though theoretically they are there. This has got no meaning. So only this. So 0 plus 1 will be 1. 0 plus 1. Now, from here, this place, again, see, these 2 paths are non-existent. So what is your available list? Here, you see, you got your 1. And there is 2 here. So 2 plus 1 is 3. Come here. Again, these 2 are non-existent. So only this path from here you can go. So what is here? 3 plus this 6. Now this 4 is there. Again, only this path is available. So the simple distance is the 4 plus this 6. So 4 plus 6 is 10. What was the simple distance? Simple distance was 0, 1, 2, 3, 4. But the cumulative distance is this. Now let's do the same for this part. So again, to reach this, you have this. These are not available. Only this path is available. So here again 0, 1, 2, 3, 4. So let's, since this part is only available, so 1 plus 0, 1. Again only this part is available. So 2 plus 1, 3. So again 3 plus 3, 6. 4 plus 6, 10. So first row, first column of cumulative distance matrix we have calculated. Now let's start wherever. Let's say this, from this. Now you have options. This, this. Three options you have. This distance we already know. Let's put the distances first. What is this? 0, 1, 2, 3. So what is this? 0. If I take 0 plus 1, the previous distance was 1, 0 plus 1 is 1. Let me use different color. So this part will give you 1, 0, 0 will give you 0. Again 1, 0 is 1. So you have a choice between, so what is the minimum? So there are three distances now, cumulative distances coming up. 1, 0, 1. The minimum one is 0. So your this will be your cumulative distance. This will be your cumulative distance. Go here. Again, find out what will happen. 1, 3, 0, and then 1 is there. Obviously, this is the distance. 1 plus 0 will become 1. 1 plus 1 will become 2. 1 plus 3 will become 4. So the minimum distance is 1. So this will be your, like this it will continue. You can fill this row up. Once you fill this row up, again you can start from here. You have three options. You fill this entire thing. Once you fill that up, then we can find out the path, the optimum path that we can take. So we'll discuss that tomorrow, and go to that video again. I hope it will clarify your doubts. So tomorrow we'll finish this up, DTW, and on 28 we'll have the minor test. So that's it for today. Please give your attendances. Please don't forget to give your attendances. And so you can, just a minute, exit the lecture. You can exit the lecture. Hello everyone. If I'm audible and if you can see my screen, then please type Y in the comments. Okay. So we were discussing about dynamic time warping. Hope you watched the video I shared yesterday. Again, in order to help you get a better idea. So we will watch some more videos today, but first let me clarify the things that we were discussing yesterday again. So what we are speaking about, it is in speech recognition. We have a technique for template matching. We have a technique for template matching which we call as dynamic time warping. So we gave an example of let's say Amazon Alexa, Google Home, or any other let's say Siri, Apple Siri, whatever it is. Uh, let's say there are certain phrases they have, 4 or 5 phrases or more than that, depends upon the capacity or how well the model is built. Let's say 4 or 5 phrases are there. Whenever you speak a certain phrase, there are 4 or 5 phrases that are standard phrases that are stored in Amazon Alexa or any other speech recognition system. A closed set, this is called a closed set, means a fixed number of phrases or sentences it can recognize. So you have this 4 or 5 phrases there, and then you utter one of these phrases, some command, some phrase. Hey Google, open Netflix, maybe something like that. Maybe certain commands. Then whatever utterances, the speech signals that are stored, can we match it? Can we match it with whatever you have uttered? Obviously, if you are uttering the same phrase, there should be much more similarity between that particular phrase compared to the rest of the phrases, whatever the rest of the phrases are. And so this is called template matching. So there are certain templates stored, and you are testing the system with a particular one of those templates you are uttering, and you are matching. In this process, you will have something called alignment. We will need to do something called time alignment, and we'll also get to see something or something called warping path. These are the two main things. So yesterday we were discussing how we can use a cost matrix to to what is called realize this dynamic time warping algorithm. So we are discussing. We took a simple example of, let's say there are two signals like this: 1, 2, 3, 4, 5. These are the values it has. This signal. This is some time. This 1, 2, 3, 4, 5, or let's say n discrete time. Let's say again same 1, 2, 3, 4, 5, and we built a matrix like this. This is like the individual. If I say this is S1T, this is S2T, or XTYT, whatever notation you want to put. Let's say S1T is here, S2T is here. In this case, there are same number of points, but it may not be the same, because let's take an example of a speech signal. It's speech signal, the same phrase you speak, whatever be the phrase, your friend might speak at a he or she might take a different time. He or she might be speaking slowly, or has a naturally faster rate of speaking. That's a simple example. So even you, when you are uttering the same signal, it's never of the same length, never the same duration. So it will always be, the duration will always vary even if the signal is the same. But in this hypothetical scenario, yesterday we were discussing how to build a cost matrix. We took this simple example that two exactly same signals, 5 points are there. What will happen? Let's say this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we uh, we build this 0, because 1, 2, 3, 4, 5, 1, 2. 3, 4, 5. So individual distance between the points. So like that. So these are the individual distances. From there, we could individual or point by point distances, costs, point by point distances or cost or distance. And then we build a cumulative distance matrix. We found a way that at each point we have three paths available. Which one to take based on the cumulative distances and how to calculate the cumulative distances. We went through that last class. So we'll again revisit those concepts. Today we will watch two, I think, really brilliant videos that I found in the internet, and then we'll see if we can finish wind up today, or maybe the next class will wind up the DTW algorithm. So let's go to let's see where I have so uh, what I was saying was, let me again pull this out. So the objective is template matching. So you have two sentences, two phrases. Let's say whatever. How are you? Let's say how are you? And someone, speaker one, speaker two, you're speaking. So we expect that the characteristics of the speech signal at different points of time will be similar compared to, for example, another sentence, who are you? Or what are you doing? Or what are you doing? Let's say, what are you doing? So obviously this is a longer, it might be, might not be longer, it depends on the rate of speech and all that. But obviously the, because different vowels, different speech sounds are there, both of these sentences, this sentence and this sentence, they will be quite different. And we expect that if you are uttering the same phrase, then we can do a template matching. The issue is our lengths will be different, lengths of the speech utterances will be different, and so we have to match appropriate regions of the speech signal. This is what dynamic time warping will do. So we'll watch another video which will give the algorithm. I will discuss this algorithm again in the next class when we will conclude it. I realize that it will not be possible to complete today. So let's watch. So yeah, please continue watching the video. There is again 10 more minutes left. So you have a next class. I will not stop you from this one, but please go through that video. It's a wonderful video. That's why I shared with you. Tomorrow is minor, and we'll finish off dynamic time warping next week, first week. Then we'll move on to something called HMM. So uh, please give your attendances in the Excel sheet, and please exit the lecture. Screen is visible, I suppose. Yeah. So I hope you watched the last video that I shared. It was so good. It's almost explains DTW better than any other probably teacher could explain it with good animation and all. But I will extend it to uh, how it is implemented in speech processing. So what I will do, see this algorithm. Generally, I will take it from a textbook or something, but it was such well explained. I took a snapshot of that. If you watch the last video, it's a snapshot of the algorithm he was explaining. The teacher was explaining. So let me go into detail regarding what's happening here. So just assume now I will do in terms of speech. So you have a speech, whatever utterance you uttered. Let's say, "How are you?" Let's say, "How are you?" You spoke, and we are trying to match against "How are you?" But obviously, it will be different for different people, or depending on your emotion and all that accent and everything. It will be different. So our goal is to match these two. In the example that was shown in the video, two people were walking. So they were trying to match the gait. It's called gait, or just yeah, gait. How they are walking, they are trying to match. Obviously, both are walking in the same manner, but there are some differences. So here also, you see these regions you have to match with these regions. These regions probably you have to match with this region, because everybody is speaking. They are speaking the same phrase, but everyone's way of speaking is different. So this is the uh, yeah, this is the main objective of dynamic time warping. So to dynamically match two sequences. Now this could also happen not only in speech, also it could be, let's say, genetics to DNA sequence matching, it could take place, and so on and so forth. But to match to sequence, that is the objective. So in case of speech, we are not going to do, you saw in that video, there was like two curves, point by point, they were matching. We are not going to do point by point matching. One single speech signal, if it is a 8 kilohertz speech signal, that means 8,000 samples per second. You do not do that kind of thing. We will do frame by frame analysis. There will be frames of certain size and a frame shift. You'll shift the frame, generally 20 by 10, 50% overlap, or whatever, 75% overlap. It's up to you. But frames. So what we do, we have frames. From each frame, we have then uh, features. It could be MFCCs. So you could have frames. You will have frames. From each frame, you will have features. So let's say for the first, you have some M frames. You have N frames. And for each of these frames, you will have some, let's say, 39 dimensional MFCCs. 39 dimensional MFCCs. Indirectly, what we have, two sequence of vectors. You can say X, you can say Y. two sequence of vectors. One is, sorry, x1 to, let's say, xm, y1 to ym. We have to match these vectors with one another. That's the goal. We are not going to match the curve as in a sinusoid. Simple example, hypothetical example that we saw. We'll match the features, match each of these features. So let's go to the algorithm now. So this is the goal. Where was it? Yes. Okay, so here it is written x1 to n, y1 to m. So let me change it here. So x1 to n, let me make it. And y1 to, yeah, okay. x1 to n, y1 to m. Let me make it uniform so that there is no ambiguity. So you have this x, or you should write it as a matrix now. So x1 to xn, yn. Two unequal sequences. You extract the features frame by frame, you get two unequal sequences. Now when I was explaining, I talked about two matrices. One is one individual cost matrix and one cumulative cost matrix. This is actually, sorry, this this is actually a cumulative cost matrix, because as you will see, we will sum up, we are adding up. As you fill up this matrix, we are adding up the distances. That's why cumulative. Now why I said about individual or individual cost matrices, it's not necessary to create that, but it helps you understand better. So here, let me do like this. So the individual cost matrices here, if you put let me see what they have done. Yeah, so x and y, they have put it like that. So let me put x and y. So one, let's put 1 2 3 4 n, and this is 1 2 m. So this is y, this is y, and this is x. So for each vector x1 or xi with yj, you can find the individual cost. What is the distance between them, you can find. So you can find from this something ixj. Basically, what you are finding, xi minus yj. Now this distance, this is a simple Euclidean distance I am talking about. You could have many other forms of distances, various types of distances are available, but a Euclidean distance I am talking about here. So this you can fill up. So dij you can fill up. And our goal is to find a path to match the templates. To find a path from this last these two signals, these two frames, let's say last frame of both the signals to the first frame of both the signals. Last frame of both the signals to the first frame of both the signals. We have to find a path so that the individual points, which frames are matching with which frames. So we match those frames and calculate distance from them only. That's the goal. So this you can easily find the Euclidean distance for I belong to 1 2 and j belong to 1 to m. You find all the distances, fill up the matrix. What is being happening here? It's better to have this distance because it serves as a lookup table to calculate this cumulative distance. So when you are here, we talked about how we can get all these distances. Okay, so when you are here, obviously there is only one distance. There is no concept of any cumulative distance again. Only d11 is there. But in making the algorithm, you will find what they have done, or when you write the algorithm in code it, it's people code it like this. They put, see here 1 to m, they put another 0 and 0. They append one row and one column, and they put all this infinity. Only this portion they give a cumulative cost as 0. Now you are here, the first. Obviously, you have no path. You will start from this place. So why will you choose this? This is having infinity. Why will you choose this? This is having infinity. You have put a 0 here. That means cumulative cost does not add up. 0 means if you add the distance, nothing happens. So you choose a path like this. You choose a path like this. Now, when you calculate the cumulative distance, you will go to here. One by one, you can do. This is infinity. This is infinity. You will obviously go from here. You will add this, whatever you have here, and then this distance, d12. This individual distance you will add along with the cumulative distance of your previous point in the path. Then you come to here. Again, you see there are three paths. Why will you choose? You will choose the minimum distance. The path which gives you the minimum cumulative distance. You obviously, that's why they have put infinity there in the algorithm. That's the goal. It's a software code basically. So now again this will come. Now similarly this will happen in this case. If you see here, where you cannot come from all this. Only way is this. And how will you get to here? Well, this is the cumulative distance that is there. From that distance, this minimum cumulative distance, this is the only best choice you have. And what will you add to this? This individual cost. This you will cost. That's why I prefer having two matrices side by side. At least when you code it, write a program of DTW, you will do it like this. It will be much easier. So similarly, you come here, you find it. Now, when you start here, when you are here, let's say, now you have options. You could have this distance minimum or this distance, this distance. We don't know which one. Any three of this could be a minimum distance. And then you have this individual cost. Add this individual cost and the minimum cumulative distance from the previous point in the path. What is the minimum? Like this, you fill up the whole table. This is how you fill up the whole table. And then let me go back now. That's because the example is so good. So here, not the example. Yeah. the previous video, whatever algorithm has been written is so good. So here they have not shown the, sorry, here they have not shown this individual cost. They have not drawn. I have drawn because I think it makes it easier. But this is what is happening. Length is 7 of one sequence, one is 6. And here finding a path from 0, 0 to the last. Finding a path from 0, 0 to 6, 7 or 6, 7 to 0, 0. You have to end at the last points of both the sequence and the first points of both the sequence. That is mandatory. So they filled up all the cumulative distances. This is what they did. If you had another dij, or here dxiyj, same thing. Which is here they have, because they have used a simple example, a simple what is called absolute distance or absolute difference between the vectors. In case of multi-dimensional vectors, we will not use absolute distance. We will do some other metric. For example, a simple one is Euclidean. So now you have this distance. You can look it from here, or during the algorithm you do it. How you design the algorithm, it's up to you. You can have first create a matrix, or during the construction of this cumulative cost matrix, you at that time itself you find out the individual distance. It's up to you. So what's happening is I2j, these all this, they have made it infinity so that there is no path available for the first point. There is no other path available, and this row and this row, there is no other path available. See here, what other path? This path is non-existent. This path is non, only this is the path available. So this is a algorithmic way of avoiding uh, that, or algorithmic way of putting it is that improbable scenarios. So you have at any point the individual costs and the minimum of these three. What are these three? If this is ij, let's say this is ij or xi, xj, whatever you say, this is the point. Oh yeah, I and j. Let's say ij. This is the ijth point. See, di minus 1, j minus 1. This is the location. Di minus 1, j. So di minus 1, j will be this. And di j minus 1. Di j, sorry, yeah, di j, j minus 1 will be this. Di minus 1, wait, yeah, di minus 1 j. J is this. This, yeah, di minus 1 j. So these are the three parts. Basically, this. That's what is happening. And you are selecting the minimum. Now, once you have got this matrix, now it's really easy to find the path. See this 0.5. From the last point, you will have to traverse to the first point. Look at all this. Which is the minimum one? You have three paths available. Which is the minimum path? The minimum. Take the minimum. From here, now look again, three different points. Which is the minimum? See this. From here, once you reach this, which is the minimum? This. Again, like this, you come here. The algorithm ends here basically. 1, 1. But again, this is just for algorithmic conformity to make your what is called pseudocode format algorithm. You do this. So this is the algorithm. So initialize with an appended row and appended column with all infinity. D00 you put as 0. Then from 1 to, see, from 1 to 7, not 0 to, so 1 to n, not 0 to n. And similarly, j to m, not 0 to m. You traverse this loop and then trace back from that gives your path. Each point on the path, for example, this point, what does, when you are traversing this path, what does this mean? This means this, that this seventh point of the sequence, or let's say seventh frame, is matched with fifth frame. Those are two sequence of unequal lengths. You are matching one with the other. So you will definitely have to find out which points to match to with what. So this is what is going on. So these are, and here please note, this distance could be any distance, not just this. In this simple example of walking, he used a simple absolute distance, but for a multi-dimensional point, multi-dimensional data, you will have to do other, you have to find out other forms of distances, for example a simple Euclidean distance. So let's now go ahead and give this a more mathematical formulation, a little bit more mathematical formulation. Let's see this. So what's happening here? What are these? These are different paths that are possible. See, in this simple DTW, the cumulative distance that we have, cumulative cost matrix. You have a cumulative cost matrix, and at every point in simple DTW, you are choosing this simple three-part scenario. And even during the creation of the matrix. But why not have more complicated parts? What stops us from having more complicated parts? Because see, in this scenario, it could be possible that we traverse something like this, which is not very good. It is possible. You have a situation something like this. If you have a this kind of path, sorry, this kind of path. One way is to, for each path, you can give a weight. When you are calculating the cumulative distance itself, you can give a weight. You can say this is 0.5, 0.2, 0.3, something like this you can give. That is one way to tackle it. On top of that, you could have different parts. Why not have parts like this? What stops us from having parts like this kind of parts? At every point when you are creating the cost matrix or when you are traversing the path, you could have all these kinds of different parts. These are some parts I am showing. This is the simplest one, DTW type 1. So this will prevent some of the issues in simple DTW. Having weights plus this kind of different parts. So with that, let's go to the formal definitions of DTW. So what we have are two patterns, X and Y. We have two sequences of vectors, one of length tx, another of length ty. Two speed signals, you have taken frames from each frame, whichever is one is longer than the other, obviously, even if you speak the same phrase. So if a simple strategy is, let's say, one is 1.5 length speech signal, another is, let's say, 2 second speech signal. Let's imagine. So similarly, you will have same number of, means frames will be of equivalent ratio. Let's say one has 10 frames, another has, let's say, 12 frames or 15 frames. So what you could do is take a simple ratio. You put 1, 2, 3, 4, 10. So one is based on this ratio, let's say 12 by 10 or 15 by 10. Let's say imagine this is 15 frames are there. So based on this ratio, you can round off and select every other alternate frame. Obviously 1.5 frames you cannot. So let's say every second frame you are taking, matching with the previous. That is a simple strategy you can do. That will be called linear time alignment or linear time normalization. So what you are doing in that case is this. Individual distances you are taking, and what this based on this length of the two sequences, you are comparing the frames or the individual points. This will be called your linear time alignment. This is not dynamic, this is linear time alignment. But obviously, this is not going to work out very well. There are too many variabilities, too many independent factors changing, which impact the speech signal or any sequence, let's say. So we need another way to compare. So what we do is this. We imagine that we have a sequence of length tx, another of ty, but we will match them with t. T individual points of them we will match. T will be less than equal to tx, comma ty. So which are the frames or points we will match? Those are given by this. We will have to find a function phi x. We will have to find a function phi y such that they output what are the indices of the individual sequence we have to compare. So when you do that, you get this is what? Ix, Iy. These are the ones we will compare of the two sequences, the individual points of the two sequences we will compare. And then if you sum them up, you get a cumulative cost. What is the MK here? Say, you can give all this when you are finding or comparing individual points, it's basically finding a path. So you can give some weights to the path that is being taken. That's what mk is. And m5 is a normalizing factor. You see, if you compare two huge sentences, distance will be huge. So to normalize that, it's a normalizing factor to bring all different comparisons to an equal, comparable level. That's it. So the main important point is this phi x and phi y. So we have two functions, phi x and phi y, which will tell us which are the individual points in x and y sequence we have to compare and match. And what is DTW doing? DTW is doing, uh, let me see if I can hide this. Yes. So DTW is doing this. There could be different functions, phi x, phi y. There could be many different choices of, but we have to find the best phi x and phi y so that our cost is the minimum. That will give us the optimum path, so to say. This is what DTW is doing. That's the goal of DTW. You have two sequences, x and y, length tx ty. We want to match the individual points of those two sequences because they are of different length. So we find out, we need to find out two functions, phi x and phi y, which will tell us which individual points of both these sequences we have to compare and match. When we find the best phi x and phi y, we get the best match. Indirectly, if you put it in a matrix, you will find the most optimum path. So that best phi x and phi y that you find, that is the goal of DTW, dynamic time warping. So here is an example. So T points, you have already fixed that we'll compare T points. One is of length Tx, another is of length Ty. This is the mathematical formulation. Okay. One is of length Tx, other is of length Ty. But we'll compare, find out T points which we can match. So those individual points, Ix and Iy, are given by these functions. And so you will compare those individual Ix points given by the function with the Iy points given by the phi y function. And then you get a path. Some points you see will not be compared. Only some points will be compared. You see, what is warping? Warping is distortion. This path is distorted. It is not a straight line. Hence, it's called dynamic time warping. The warping word is included because if you see the matrix, a path that we find out eventually, it is a distorted path, not a straight line. Dynamic because dynamic sequences, two different sequences we are matching. So this is what DTW is all about. This is the goal, mathematical goal of DTW, and the algorithm we have discussed in the last 3 lectures what it is. Now, what is the advantage and disadvantage? Well, advantage, you can see it's a very simple algorithm. It is simple to understand, at least simple to implement and understand. Disadvantage is time. See, in DTW, there is nothing called training phase. Is there any training phase here? No. All you are doing is at the testing time, you get a signal, you extract the features, and then during testing you have to do this DTW process during the testing time. If you have a neural network or a GMM, or we'll discuss HMM and all, you have a big training phase in which you train a model with lots of data, lots of time. In a testing phase, you extract the features, put it into the model, it will spit out an answer. But in DTW, testing time is large. This is the principal disadvantage of DTW. Now, there are other disadvantages as well, which you can imagine. Suppose the same speech somebody is uttering, let's say 2 seconds it took, and somebody is uttering the same speech at 4 seconds. He's a slow speaker. Then simple DTW, which is having this kind of, at every point of time you are finding this simple DTW, three different parts, it might not work, because one is quite a long sequence compared to the other. If those are comparable sequences, let's say one is 2, another is 2.5, this will probably work quite well. But if the sentence sequences are very, length of the sentences are quite different from one another, then this simple DTW mechanism might not work well. Because indirectly, what you are asking one point to be matched with something very far away. But here, we are looking at only the adjacent points. So you might have to find out different complicated paths. But if you find a fix on different complicated paths, but because speech is time varying, only one portion of the speech somebody spoke slowly, somebody again, but spoke in a normal or fast manner, other portion of the speech, it could create trouble. So when the speech lengths are more or less comparable, or uniformly spoken, DTW works well. Otherwise, it could have issues. And other than time, testing time is a big no prawn. That's a disadvantage for DTW. So that's it. Nothing more to speak on DTW. Please go through this algorithm. That video was really good. Go through that once again along with that lecture. I will upload all the videos together in a single file for DTW. Give your attendances online, as you know. So that's it.